You hear it everywhere. Quantum computing will change the world. It'll break encryption, discover new medicines, and create materials we can't even imagine. But while the headlines scream breakthrough, the reality is far more nuanced and, honestly, far more interesting. Today, we're not just talking about the hype. We're stripping it away to reveal the fundamental, non-negotiable limitations of these incredible machines. Let's get real about what quantum computers can and, more importantly, what they can't do. First, let's quickly cover the promise. A classical computer uses bits, which are either a 0 or a 1. Simple. A quantum computer uses qubits. Thanks to a wild quantum property called superposition, a qubit can be a 0, a 1, or both at the same time. And with another property, entanglement. You can link qubits together so their fates are intertwined, no matter how far apart they are. This allows them to explore a vast number of possibilities simultaneously, making them seem exponentially more powerful than our trusty laptops for certain tasks. But, and this is a huge but, this incredible power comes at a very steep price. The single biggest challenge, the great enemy of quantum computing, is a phenomenon called think of a qubit in its quantum state as a perfectly still, delicate bubble. It's beautiful, but incredibly fragile. The slightest disturbance, a tiny vibration, a stray magnetic field, even a microscopic change in temperature can pop that bubble. This interaction with the outside world is decoherence. It forces the qubit to collapse from its powerful 0, and 1 stayed into a boring classical 0 or 1, losing all its quantum information. This is why quantum computers are housed in these massive chandelier-like structures called dilution refrigerators, which cool the qubits to temperatures colder than deep space, just fractions of a degree above absolute 0, simply to protect them from the noisy, chaotic world. So, the next time you see a picture of one of these amazing machines, don't just see a futuristic computer. See a life support system, a desperate attempt to isolate a fragile quantum state from reality itself. This physical instability is not a minor bug. It's a fundamental feature of the universe we have to constantly fight against. Now, let's tackle the second major myth. The idea that quantum computers are do-everything machines that will make classical computers obsolete. This is completely false. The truth is, quantum computers are specialist tools, not general-purpose ones. Your smartphone is brilliant at browsing social media, sending emails, and watching videos. A quantum computer would be terrible at those things. They only have a speed advantage for a very narrow set of problems. The most famous example is Shor's algorithm, which is incredibly efficient at factoring large numbers. This is what threatens modern encryption, which relies on the fact that factoring is extremely hard for classical computers. Other areas where they show promise are in simulating molecules for drug discovery or designing new materials, because these are naturally quantum systems. But for the vast majority of computational tasks, from running a database to playing a video game you're classical, CPU or GPU is and will remain far more efficient and reliable. Think of it like this. You wouldn't use a Formula 1 car to go grocery shopping. It's overkill, impractical, and designed for a very specific track. Quantum computers are the F1 cars of the computing world. This brings us to our third, and perhaps most daunting, hurdle, the overwhelming problem of errors. Because of decoherence, qubits make mistakes. A lot of mistakes. Their error rates are millions, even billions of times higher than the bits in your laptop to build a truly useful, fault-tolerant quantum computer. We can't just use these physical qubits directly. We need to bundle them together to create a single, stable, and corrected logical qubit. This is the basis of quantum error correction. The overhead is staggering. Current estimates suggest you might need hundreds, maybe even thousands, of noisy physical qubits just to create one high-quality logical qubit. So, When you hear a company announce a chip with a few hundred qubits, remember that we're still miles away from having a few hundred logical qubits, which is what we'd need for many of the most exciting applications. This reality has a name: the NISQ era. It stands for Noisy Intermediate Kill Quantum. It's an honest acknowledgement of where we are right now. We have quantum computers with an intermediate number of qubits, say 50 to a few hundred, but they are incredibly noisy and error. We don't have enough qubits yet for effective error correction, which severely limits what we can do. The machines we have today are essentially prototypes. They're amazing scientific instruments that allow us to explore quantum mechanics and test simple algorithms. But they are not yet the world-changing devices promised in the headlines. We're learning to drive the race car, but we're still in the practice laps, nowhere near the championship race. And this leads to the colossal challenge of scalability. Building a quantum computer with millions of stable, interconnected qubits is one of the greatest engineering challenges of our time. It's not just about adding more qubits to a chip. How do you control each one individually? How do you wire everything up without introducing more noise? How do you keep this massive, complex system at temperatures near absolute zero? Every qubit you add increases the complexity and the potential for error exponentially. It's like trying to conduct a perfect orchestra where every musician is prone to playing a wrong note at any moment, and adding more musicians just makes the chaos harder to manage. The engineering required to solve this is just as monumental as the underlying physics. So, let's bring it all together. Is quantum computing just hype? No, absolutely not. The science is real, and the potential is immense. But the limits are just as real and are rooted in fundamental physics. First, the delicate nature of quantum states makes them incredibly prone to decoherence. Second, they are specialized tools, only useful for a narrow class of problems. And third, the massive error rates require an enormous overhead for correction, a barrier we haven't yet overcome. The journey to a fault-tolerant quantum computer will be a long and gradual marathon, not a sprint. We will see incremental progress, not a sudden revolution. It's a field defined by brilliant science and Herculean engineering, but we must be realistic about the timeline. So what surprised you the most about the real limits of quantum power? Was it decoherence, the error correction overhead, or the fact they won't replace your laptop? Let me know your thoughts down in the comments. And if you appreciate this honest, hype-free look at the future of technology, please give this video a like and subscribe to Dev. Thanks for watching!